These are each going to be important to know. I'd say especially the side splitter theorem, this first one. Okay, so the name is the triangle proportionality theorem, but it's more commonly just called the side splitter theorem. Both are good. Both you could use as like the reason, if we're using it as a reason in our proof, you could write either one. It basically says this: take any triangle, one triangle, draw in a line that is parallel to one of the sides of your triangle. So I could have, in this triangle, I could have drawn it in parallel to this side. It would have been like that. Okay, but I chose parallel to the bottom one. So just draw in a parallel line. And what it does is it separates the sides proportionally. So let's see what I want to say here. If a line is parallel to one side of a triangle, okay, it certainly intersects at two distinct points. It can't come up short. Then so it can just be like that. Then it separates the sides into segments of proportional length. So, okay, so you said there's a small triangle and then there's a big triangle? There's a small triangle, then the big triangle overall. Well, we're going to be able to show those are similar. So we would know like this segment over the whole thing is similar, is proportional to that segment over that whole length between the small and big triangles. Or I could have used these as well in that ratio. But what the side splitter theorem says is it makes it another nice conclusion. It says this ratio to this one is equal to that to that. So that your parallel line separates those sides proportionally. Go ahead. Okay, so I put like BC over AB is equal to DC over DB. So not only do you know like CB to the whole thing, but you actually just know that parallel line breaks it up proportionally, that to that and that to that. It's kind of nice. Any parallel line breaks up. Triangle proportionality theorem. So the converse is also true. This is not the other theorem we're going to prove. This is just, it goes along with this one. This one says if you know that ratio from that segment to that one is equal to that, then you know that this line inside is parallel. So it says this, like suppose you know this is 8 and this is 4 and this is 10 and 5. You do the ratio 8 to 4 and it's 2 and 10 to 5 and it's 2. Therefore you can conclude BD is parallel. So that's the converse, that's the reverse. This one says there is a parallel line, these sides are proportional. The converse says if these are proportional, equal ratios, then the line is parallel. So just going to flip that over. We're going to prove not the converse one, just the regular one, the side splitter theorem. I started, this is an OST one, and I've always liked this one. I think it's a good one. So guys, here, let me give you an overview of what we're trying to do, so you can kind of see where we're going to go. You see it says XR to RQ and SY, SQ. We're trying to show that ratio is equal. What we're going to do is show the triangles are similar, the small to the big. And then what we'll do is we're gonna want these individual segments, and so we're gonna have to do some segment addition and do a little simplifying. I've given you all the statements here, and we're gonna fill in the reasons. We'll also think through why the statements are true at the same time. All right. So first goal is to show the triangles are similar, the small and the big one. And what we're provided is the triangle and one parallel line. So let's show the triangles are similar. First is given, of course. Second, we know angles 1 and 3 marked up there are congruent. Bless you. Bless you. And then we know marked up there 2 and 4, those are also congruent. Anybody raise their hand and tell me why we know that? Just past true things we know. Anybody else? Let's go, Doug. Thanks. Yeah, thank you. They're corresponding, right? You could draw it out like this if you want. See, like 1 and 3 are these two. Yes, thank you. Corresponding angles, and you're right, it's postulates, zip theorem. Those both pairs, 1 and 3 are corresponding, so they're congruent. 2 and 4 are also congruent because they're corresponding. Sounds good. Would you agree that the small triangle right there want 2 angles, and they're congruent to the big triangle 2 angles, right? We have 2 sets of congruent angles. That's all we need to show triangles are similar. That's the best one. So the triangles are similar. Angle, angle. So that was really goal 1, right up to there. Show the triangles are similar. Now what we'll be able to do is get some ratios that we can work with. So, thoughts so far? Very good. So triangles are similar. Now what we need to do next is we want to show QR and RX. Well, I can't write a ratio between those yet. So I'm going to look at the small triangle and choose this side, RQ. And looking at the big triangle, we're going to choose XQ. So I'm writing ratios now. So I guess I did the big one first. In the big triangle, XQ matches up with RQ. That's a ratio, it's true. Equals, over here, YQ and SQ. Those are another ratio that's true. Now, I think this is going to be the first time we've used this one. Remember when the triangles were congruent, we used to say CPCTC, that like the sides were congruent or the angles were? Same idea here. If the triangles are similar, we know that the sides have equal ratios, that they're proportional. There's 2 things we can write here. Let me write both those first time. Do you remember CPCTC was actually a definition of congruent triangles? Right here, same thing. So we can write, one option would be definition of similar triangles. Or you could write, when we say CPCTC, we're saying the corresponding parts of congruent triangles are congruent. Here, you would say the corresponding parts of, I should say sides, I'm sorry. The corresponding sides of similar triangles are proportional. I write both proportional. Sorry, not room. Are proportional. I read both. They're both true. I really would have gone with this one overall, but I've started to see one release test question. They did this. They wrote it out in words. So I want you to know what it really. It's just saying the sides are proportional or equal ratios. So you can write the ratio. Yeah.
So if we were in the converse, going from the proportional sides to figuring out that it's parallel, would we use the same results? Or like?
No, usually backwards it's at least somewhat different. Yeah, it's at least somewhat different. I think on that one I would say that since the ratios are equal, we'll probably be able to show the triangles are congruent. It's kind of backwards. We'll be able to show the triangles are similar, I think by SAS, similarity, and then we'll have corresponding angles. So usually mostly reverse, but not totally. It's a good question. So corresponding sides are proportional with equal ratios. All right, now what I need though is I need XR and RQ. I don't even have anything yet with XR. Right, there's nothing in here with XR yet. So what I need to do is break it up, and I'm going to do segment addition. To say that plus that equals the whole segment. XQ equals XR plus RQ. Same thing on the other side. What did I name it here? YQ is equal to YS plus SQ. I think I already gave it away here in segment addition. That's just adding the segments. So the reason we went this route is I didn't even have XR in there, and in my final, what I want to prove, I need to get XR in there somehow. Well, I can do that by getting segment addition. And from here, we're kind of manipulating the equations. So it becomes an equation, and we use a lot of the properties. So the next thing we'll do is we look at this equation in 4, and I take this one, and I plug it in place of x cubed. If you look down here, I replace that with xr plus r cubed. I take this one, and I replace it up there in place of y cubed. Plugged it in. So, substitution. Substitution property. Let's see, we're almost done here. What they're going to do next is put each of these over r cubed. So that divided by r cubed and r cubed divided by r cubed. It's kind of like if you have 2 plus 6 over 2, you could really write it as 2 over 2 plus 6 over 2. You could break it up if you want to. Or like maybe 2x plus 6. You break it up into 2x over 2 and 6 over 2. So we're just rewriting how it looks. We're kind of simplifying. There's no property we apply besides just a simplification, which is another substitution. I wrote an equivalent form, which is substitution. I substituted in something that's equivalent. What's anything divided by itself, like r cubed divided by r cubed? It's 1. I'm just saying when you work it out. You're right, if it was congruent to itself, then you could just. That's 1. Same thing over here, right? SQ over SQ is 1. So, they did not divide. We did not divide both sides. We simply just said, well, what's equivalent is 1. We substituted again. We just replaced that RQ over RQ with 1 and SQ over SQ with 1. A lot of substitution here. Finally, the 1's disappear because we're subtracting 1 from both sides. That's it. We reach our conclusion, which is XR over RQ, YS over SQ. They have released, just so you know, they have released this question as a one of the ones that test released one. I think it was a fill in the blank. You didn't have to do every step. It was only some of them, but still, it's a good one to know. Anything I can answer on that one? Questions on that? Okay. Again, this one will come back. I already put it on the review. It's one that we do need to know. So let's apply that one below, and then I'll tell you the one other theorem will prove that one as well. So let's use the triangle proportionality theorem to find the value of A in this diagram. So since the arrows right there, right, means the sides are parallel, we can use the triangle proportionality theorem, side splitter theorem, to write a proportion. 2 over A plus 4. And then I can do A over 6. It's really what we're going to have to do. I mean, there's no ratio we could easily see between these, so we pretty much have to do this. And we're going to cross multiply. 2 times 6 is 12. Remember here, it's really A times A plus 4. So you have to distribute. A squared and then 4 times A is 4A. We do get something with a square, x squared, x, and a number, so I'm going to have to subtract 12 and factor. So let's factor the trinomial. 2 numbers that multiply get negative 12. Add to get positive 4. what's out there? 2, you say negative 6?
and negative
Yeah, positive 6 and negative 2. Okay, so we get negative 6 when we turn them around, and 2. This is one where it wasn't just a proportion. We had to, it's actually relating to a segment length. If we put in negative 6 here for A, that's a negative side length. We have it. So 2 is going to be the only option that works. If I go back up here, it would make this 6, then it would make it 2. It's not usually going to be, they were actually the same. It's usually proportional, it's not usually the same. It just happens to be here. Okay, so guys, I want to tell you this. This saves us. We know the small triangle, again, corresponding angles. We know the small triangle and the big triangle are similar. Let me tell you this. This would also work. 2 over the whole segment, which is A plus 4 plus 2, which is A plus 6, equal to A over this whole segment, which is A plus 6. That would also work. Okay? But what the side splitter theorem is, it saves us from doing that. That's a little more work, I'd say. It just says, all right, this to this, this to this. It's an easier proportion. Let's see. So that's triangle proportionality theorem. I'll tell you one more theorem for today. Anything else I can do with that one? Okay. Flip it over. And the next thing is called the triangle mid-segment theorem. And I have to tell you what a mid-segment is first. Oh. Right here, yeah. So to get to what a mid-segment is, a mid-segment is, you can kind of guess, a segment in the middle. It's really a segment formed from midpoints. It's a segment formed from midpoints is what it is. So a segment whose endpoints are the midpoints of two sides of a triangle. So for example, take AC. If I know B is a midpoint and D is a midpoint, so I'll put B and D midpoints. Suppose we knew that. If B and D are midpoints of those sides, of AC and EC, then BD would be a mid-segment. And so then, again, there's one theorem about the triangle mid-segment theorem. It's actually got 2 parts, but let me tell you about both of them. So basically this, if you know that this is a mid-segment, and by the way, it might not look like it. It doesn't look like it's in the middle, as figures aren't drawn to scale. If you know you have a mid-segment of triangle, then there's a couple conclusions. The first is that it's parallel to this side. So if BD is a mid-segment, it's parallel to one side, the corresponding side. And here's the other thing, its length is half the length of that side. So the triangle proportionality theorem was simply, draw any line, it could be this one up here, parallel, and it separates these sides proportionally. This one is, if I know these are midpoints, then these are parallel, so then the triangle proportionality theorem is also true. And this length is half of this one. So like if this is 10, then this length will be 5. So 2 parts that we're going to show. How this is half of that, and that we get a parallel line. We get a parallel line. So, any thoughts before we prove these? All right. So let me go to the next slide here. So we're going to prove part 1 and 2. And again, I'm giving you most of these. When I got this in the Smartboard, I must have accidentally copied that. Okay, so this is another one the state says to know. I think this one, it comes together nicely, but it takes many steps to get there. So here's what we're going to do. B is a midpoint and D is a midpoint. We're going to show that these two lines are parallel. Okay, this is the first part of it. And so really, guys, here's what I want to tell you. If we can get the triangles similar, the small and the big triangle, that's really, here, show triangles similar. That's really the goal. If we get the small triangle and the big triangle similar, then I'll be able to show these two lines are parallel. Okay. So let's write in most of the reasons here. B is the midpoint of AC. D is the midpoint of BC. So what I'm going to do first, since that's a midpoint, I know that this length and this length are equal. So I'm going to write AB equals BC. Since D is the midpoint, I know DC. I'm just looking at what I wrote here. I wrote DC and EB. Just trying to match it up with what I did here. Right, midpoint means right in the middle. Now, this is the definition of midpoint. Midpoint theorem says the segments are congruent. This is just saying they're equal. Definition of midpoint. Okay, so we got those two segments equal. Guys, I'm kind of going to do this similar as the last one, where where I need to bring in some other segments, and so I'm going to do segment addition and then manipulate the equations again. So that's what we're going to do, segment addition here. So I say AB plus BC equals the whole segment AC. And then we say DC plus ED equals the whole segment EC. Part plus part equals the whole thing. First it starts the same. All right, now watch this. We take these equations. They look pretty similar, 3 to 4, but we've replaced AB with BC. That's the only thing in the first step. And then here, whatever, I replaced ED with DC. All right, plugged it in. Again, these start off very similar. So I just plugged it in, substitution. Plugged it in. I could have chosen to plug in AB for BC, but I just chose BC for AB. Okay, 1x plus 1x is 2x, right? So 1BC plus 1BC is 2 lengths of BC, right? Same with DC plus DC is 2DC. Not addition, this is just substitution. When you're combining, we combined like terms, that's what we really did there. Just combined like terms. Sorry for this too, this is just, so combine like terms. We got 2BC equals AC. Now, what I'm trying to do is show the triangles are similar. And in order to do that, I know nothing I only know something about one angle. What I need to do is get some side lengths having the same ratio. And that's what I'm working towards. This ratio to the whole thing, and that ratio to the whole thing. I'm going to show that those ratios are equal. So what we're going to do is then divide both sides by 2 here in each of these. I'm sorry, not by 2, by BC. So I'm dividing this one by BC and this one by BC, and I'll get here. 2's the BC's cancel here, it'll be AC over BC. And the bottom one, same thing, I'm going to divide by BC. And so I'm dividing, so it's circular division. Okay, and then we're we're at a spot where they're both equal to the same thing, right? They're both equal to 2. So whenever things were equal to 180, or if they're equal to the same thing, we set these equal. They're equal to the same thing. And that's what I did here. It's really a substitution. Substitution property. So let me go back up for that one with substitution to the diagram. Here's what I just did. Let's get rid of that. I just showed AC, that ratio, to BC is equal to, that ratio is equal to this ratio, AC to, EC to DC. So I showed the big triangle to the small and the big triangle to the small. Those two sides have equal ratios. I got two sides equal ratios. That's good, but in order to show the triangles are similar, I need a third side, which I won't have, or I need an included angle. In the small and the big triangle, it's that angle. Is that angle a shared angle between the small and the big triangle? It's a shared angle. So I'm going to say angle C is congruent to angle C. That is reflexive. We're talking about shared side or shared angle is reflexive. Sorry again for this. I'm going to show it over here. Reflexive. And now, if I look back at my diagram, I got two sides with equal ratios and one congruent angle, and that is SAS. So the triangles are similar, right there. SAS similarity. Okay, so the triangles are similar. I'm going to scroll back up. Here's what I'm going to do to finish up is, if the triangles are similar, all the sides have the same ratio. But really what I want is I'm going to say these two angles are congruent. So I'm going to say, and that's true, any two pairs of angles that match up in similar triangles are congruent. So I'm going to call that angle CBD is congruent to angle CAE. You also call it just A. This is because if triangles are similar, then all the sides and angles match up. This is definition of similar triangles. I could write that. Or, so I'll put definition of similar triangles. Or you could put corresponding angles are congruent in similar triangles. Or. Corresponding angles in similar triangles are congruent. Normally this is the CPCTC. For similar triangles, the angles are still congruent. Alright, now why did that matter? Why did I do that? Well, if these two, those are corresponding, right? And if corresponding angles are congruent, then the lines are parallel. That was the point. So the angles are congruent, therefore the lines BD, or is that what I want? Yeah, BD parallel BD. Therefore the lines are parallel. This is the reverse theorem for corresponding angles. Converse of corresponding angles. Pasha. I'll just go back down in a minute. So first thing was segment addition, and we did a little substitution to manipulate the equation to get that the sides had the same ratio. That took a little work. Then we said they share an angle, so the triangles are similar by SAS similarity. Therefore, in step 10, these two angles are congruent, or these two. And if those are congruent, then the lines are parallel. You know, it's a little work on that one, but you know, again, any of these that the state says to do, specifically, I have to do. Again, a lot of these you got to show the triangles are similar, and then work with that and get you somewhere. What about that? Anything to clarify that one? No. I got to do the second part of it to finish up. So let's finish this one up on the next page for you. Yeah. On the next page, I'm just going to finish up the second part. We start with the same thing. And instead of showing that these lines are parallel, I'm going to show that this segment is half the length of AE. Okay, I'm going to show it's half the length. Now I'm going to yeah, okay, this is good. So I'm going to show that it's half the length. I'm going to start with the fact that we knew the triangles were similar from the last one. Okay, part one, we knew the triangles were similar. So the triangles are similar from the last one. We knew that. So I'm going to write a ratio. AE matches up with BD. That ratio. And equals, what is it, AC to BC. Right? Big triangle to small for the blue. Big triangle to small for the red segments. So I'm writing a ratio. This is definition of similar triangles, or I'm going to write corresponding sides of similar triangles are proportional. Basically, I can write equal ratios. Right, the sides have the same ratio. Guys, I'm going to look back from the last proof that we just did. AC is because it's the same thing we started with. AC over BC, right here, was 2. So I'm going to plug that in. AC over BC is 2. Certainly just substitution. Okay, we had to do the first proof in order to get to this one. Okay, again, I'm looking for BD being half of AE. And I have BD and AE in the same equation. Right, I have them both there. All I'm going to do, I actually have it. That's what I need. I'm just going to manipulate that equation to say what I want. I'm going to take a couple steps. That's what we want, all of that, BD and AE. Just manipulate it, and soon it's going to say this. This is actually a pretty quick one once you do the last one. So I'm going to clear the denominator. I'm going to multiply both sides by BD. And so we'll have AE equals 2BD. So just clear the denominator by multiplying both sides. So multiplication. 2BD. Okay, I got AE on one side, BD on the other. That sounds good. I need the number with the AE. Right, if I look at what I want to prove, I need the number with the AE. So I'm going to get rid of this over here by dividing both sides by 2. Okay, so I'm dividing. Now, on the left side here, there's really a 1 in front of that, right? 1 over 2. I could write it as 1 AE over 2, but a better form is I'm going to write it as 1/2. That's the same as dividing by 2. So 1/2 AE equals BD. That was division, dividing by 2. And guys, that's what we want. It's just turned around. So the last step, I'll just flip the equation around. What's this one? It's been a while. Symmetric. Symmetric property. So that one, it's directly from the last one. Once we have the last proof, this one, you just look at some of the things you know and write a ratio. Change this one to 2, and we divided and multiplied, divided, and got what we wanted. So it's kind of a nice little easy thing, easy kind of corollary from the last one. So that length is half of AE. So to finish up at the bottom, basically, if you have, right, those are marked, this is a midpoint, these are marked, D would be a midpoint. This would then be 16. If that's half, this would have to be double. Oh, and the lines are parallel. Any mid-segment, parallel, and it's half the total length.